All right, welcome to the third, well, actually, this would be the sixth video on trigonometry. So, trig, it has all its applications and shapes and stuff because any shape can be decomposed into triangles. You could turn that into triangles. You could even have taken this pentagon that I just drew, made that a triangle, made that a triangle. Oh, you can always do that with shapes. And so you can always prove all sorts of geometry facts with trigonometry, just because you just have to create a right triangle. Then if you don't have a triangle that is a right triangle, like that isn't a right triangle, really. I didn't intend that to be, really. Now all I have to do is drop a line from one of these sides, and it's called an altitude line. Now you have two right triangles, and therefore you can analyze it with trigonometry. So that's just shapes. I mean, that's pretty cool enough. I mean, just take any 3 points and you can analyze it with angles and side lengths. But that's not even the full extent. Like this wave fact just gets me hyped about math. Just the fact that this extends so far, trigonometry extends so far into so many fields, just it's beyond me. But I'm going to talk most about the mathematics, so you know how to alter these functions. So I graphed a sine function. Here I typed it in on the calculator, and it plots it. So there you go. Yeah, every pi distance it graphs this wave. All right, and we already talked about that. If we increase this f, by the way, I didn't mean to write that extra parentheses. That's just f times x, not f of x like this. Different f's in here. That just means function. That means frequency. So frequency, if it's a bigger number here, if this f is bigger, then it will have smaller. If it's bigger than 1, then it'll be scrunched up waves. And you can see that here. If we make sine like 5, here's what happens. It's actually graphing only a few of them, so it's graphing really small. They don't actually have a overall wave shape like that on top. Yeah, that isn't supposed to happen. But that's just because it's graphing so many, that's just approximating it like that. Either way, so if it's greater than 1, there's a lot of them. It's small space. This whole distance, by the way, is called a period, so that's what we'd say. Small period. It's kind of different than this period. This is a full wave. All right. Either way, p decreases as frequency increases. So I'll just say p decreases. And let's call this like p of e. Sure, p of e. That's not really normal, but whatever. Yeah, decreases. And I'll just put less than. Like, it doesn't have an exact. Yeah, it's going to be less than 2 pi. Because, if you notice, a full period on a simple sine function is 2 pi. Am I right about that? Yeah. Okay. And then if frequency is less than 1, then the period is greater than 2 pi. So that's how we're going to do it. Let's just do per p. All right. And then if we add, let's go back to the normal sine function. And in fact, let's divide, because dividing is the same as multiplying by a fraction. So we're going to divide by 2, so it should be, yep, increased it. The period is much wider than it was on our calculator. All right, so yeah, this fact has been, we basically just proved it visually. You can see that happening as it graphs. And you can figure that out just because it's an x divided by 2 situation. So that's how frequency affects it. And the period, this period in this case, is what we add to it. If we add something to it, all we're doing is changing where the angle starts. All right? So let's add, I don't know, 2. If we add 2 to this, it should move this whole graph this way. It always pulls it if you add, and then it pushes it if you subtract. So if we add 2, it should push it this direction. In fact, let's make it a multiple of, pi divided by 2. We're going to add pi divided by 2 to this function. And so that should push it to here. Of course, this is an x divided by 2 function, and so it'll be wider than this, so actually push it only a quarter of the way. So I predict it will look something like this, where its peak will be at pi divided by 4. And it's going to be much wider than that. The peak will be at like pi divided by 2. So this is getting sloppy because I'm using the same color. You can see it's black. It should be something like this. Not very exact, but you get the idea. Much longer waves. Anyway, let's see what it looks like. Yeah, it starts at the top, so that's established. So it actually starts right here. And yeah, it is wider. So it basically goes like this. Yeah. I'm going to stop approximating these because my calculator does a better job at it. Let's divide by 4. Yep, shifts it a little further this way because we decreased it. Then if you subtract it, it pushes the sine function backwards. Yep, you can see this is where sine would normally be 0, but it was pushed back. So I'll push forward because you're pushing all these waves forward that direction. That's when you subtract. It's kind of unintuitive that adding would kind of pull it backwards and subtracting would push it this way. But if you ever get confused, just know that in the middle of functions, whenever you want to shift things over, you just add stuff to f of x. F of x plus a number will pull the graph. Pull and f of x. Not frequency. F of x minus some value will push it. Any graph forward. That's just the pattern if you ever see it. And that'll help you look at most functions, but we're talking about just waves. So anyway, that's the idea here. Let's go back to sine of x so we get the normal function. So now we know p and the frequency. So what is this y naught and what is a? All right, this a value, amplitude. Well, usually it's between -1 and 1. So if we multiply a number times this function, it will then go to that number. So this should actually be written as the amplitude. So a and negative a. So let's multiply something to it times it. So let's multiply 5 times it. It should have an amplitude of 5 now. Turns out I didn't realize this, but my whole graph, the extent is 5 in this direction, 5 in this direction. So it fits the whole screen in order to show it, if you see that. And so this is the amplitude, really, because the amplitude on a normal situation, just a regular sine function, is just 1. And so it goes in between 1 and -1. But if you multiply a big A, then you get much bigger waves. And if you multiply by a small a, you get waves smaller than 1. I'd write that out, but I think you get the idea. The smaller a, the smaller the wave, like smaller this direction it will be. The smaller the space is by frequency, but we're caring about right now amplitude. All right, and now let's just make it 2. So this would be an amplitude of 2. It's 2 versus the 1, like the 1 height it was. And realize that the amplitude isn't the total distance, it's only half of it, because it goes both positive, that amplitude, and negative, that amplitude. All right, so that's what A does. And last one, this one should make rough sense. In any function, if you add something to it, whatever the function is, if you add some y naught, usually that just means y like the center of the graph, whatever. If you add anything to any function, it shifts it up. And if you subtract a y naught, we're assuming y naught is positive in both these scenarios, so that this one will always be negative. You subtract it, it will shift it down. Let's just see it so you can see what I'm saying. So we have our 2 sine x. Let's add like a 5. Let's because their graph is so small. If we graph 2, 2 is now the center of our function. So rather than 0, I should write y naught here, because y naught on a normal one is 0. But yeah, rather than write pi here, I'm going to write pi divided by frequency. This would be 2 pi divided by frequency. This is getting way sloppy, but I think you're getting the idea. And that really covers every part of the sine function. You can just shift it up. And let's just do one more, shift it down. Let's shift it down by 3. Yep. And it makes the center -3. So that's what this does. And because it's periodic in this sense, then it's just determining where that center line is. That's what the y naught does. So now we've gone over this. Amplitude, it's basically half of the height of the wave. Frequency is how scrunched up the wave is. If it's a bigger number, it will be more scrunched up, smaller, more spread out. Period is basically shifts the graph. It's also called a phase shift. I believe that's actually why we use the P, because that's the more fancy term. It's kind of a phase. And then y naught shifts where the center is. And so that's the idea. Plus y naught here. Minus y naught. So y naught minus a. Alright, so that covers that. And now let's just do some fun. I'm just going to do some graphs to show you the idea of adding functions can create any signal you want. So let's go back to a regular function. Sine x. I kind of like that 2 multiplying times it. So there's our function. You get the idea. So now what we're going to do is we're going to add another sine function, but we're going to alter the frequency, the frequency here. Yeah, that's about the perfect spot on the video to put it. Yeah, let's make it twice. Let's see what it looks like. That's kind of funky. Let's have in this kind of shape. Shift over, down. Shift over, down. Alright, so yeah, you can create that. And that's only 2 sine functions together. Let's add another one. Let's alter it by doing like a phase shift, like a pi divided by 8. Alright, and let's multiply this by like 7. Sure, this will have a high frequency, so this might be way too scrunched up. In fact, let's just divide so we don't scrunch it up too much. X divided by 5, and we're adding pi divided by 8. See, that's quite funky. It's slowly going down and up, and slowly going down and up. You see what's happening. You get all sorts of weird graphs by doing this. Let's add another sine. Why not? Sometimes you have to actually add this will sound weird, but infinite sines in order to produce things like that sawtooth graph. But all you have to do, if you draw a sawtooth, let's just draw in here, just so we can sketch some stuff. So the idea of a sawtooth graph looks like this. Just forward. So if this is our graph, the center would be that y naught. That doesn't really matter too much. And amplitude would just be this distance, so that always stays the same. And the period seems to always be changing a little bit. Either way, so if you graph a normal sine like this, looks like this. Doesn't really have that sharp edge thing going on. It shows a different color than this. And it doesn't hit those points. But if you add another function to it that has a phase a little closer here, then adding them together will create something a little closer to this. I'm very estimating here. Either way, eventually we'll start adding things that make a curve that kind of follows this shape. Not exactly. But after you add enough, usually we say infinite, but don't worry. That's what you get. And by the way, if you look up Fourier transform, because that's what we're talking about here. Fourier, let's try it one more time. Just adding sine equations. Fourier transform. If you look it up, you're going to get something that looks mystical, I would say. Or just confusing. And they're going to usually like write this and then maybe like a sine of x. Or maybe they won't even write sine of x and some other fancy stuff with i's. And I don't know, it varies. Because of how you can do the Fourier transform. I'm just giving you the intuition. But integral, just a quick, we're actually going to go into calculus later. Like next video will probably be calculus wise. But if you look at sine, if you look at this sine, integral is actually like an infinite summation of tiny infinite parts. So you're adding like infinite. This is just the idea, intuition of what the integral does, just ahead of time. You're adding infinite of infinitely small parts. And so eventually you can have infinite changes in sign. Of course, this is not the exact equation of what the Fourier transform looks like. It's just not always going to have summation next to it. It's going to usually have an integral, because integral is like an infinite summation. So that's just a quick little ditty on that. For the rest of the video, I'll probably just keep messing with this. You can probably go, but I'm going to keep on doing this. Let's make one with like 1 divided by 2. Oh, I already did that. 1 divided by 3, sure. Let's make a phase shift, like a series one, plus pi. I recommend you just mess with this. It's kind of fun, just to see how complicated you can create a graph. Sometimes it takes a lot longer to graph these things. Also, there's these two ideas in physics that I didn't really go over, but if you add two sine functions together, if one crest of the wave has this and the other crest of the wave has this, I'm just writing them over each other so they don't completely overlap, then they'll just add to each other, so you'll create a really long wave. Whereas if you have something like this going on one function, and the one you add to it has this going on, it completely cancels it out, because this is always going to be the negative of this. Now, you'll also have scenarios where you kind of have a mix in between, so you don't have something bigger and you don't have something smaller or that gets weaker of a wave. So you get weird shapes because of this scenario of adding opposite kind of functions. Of course, adding them so perfectly like this isn't very common. Either way, just know that everything I say can be turned into these kind of things. Here, I'm going to write up a summation that solves this. So this is going to be a little weird. It's just a summation sign. We're going to start from, let's make our variable h, actually I, so you're used to it. Capital I. Oops. Didn't mean to do that. Let's start from like 1. Let's go to like 5. We're just going to add different sine functions. So let's create an equation for the frequency. Let's say it's going to be x squared divided by x squared plus 1. It's probably a weird function. And let's multiply times x. By the way, this should be I, because I want that to be the equation, not in terms of I. And now we're just going to add all those up, multiplying times it. And so we'll add a bunch of sine functions together. In fact, we'll have 5 sine functions. Then I'll graph them at the same time, because we're multiplying by the x value, which represents the angle. But whatever. So, I really didn't know how this would turn out, but it's just plotting it. Yeah, I don't know really what to expect. But you can get wild with this plotting. And now we have some interesting stuff happening. Well, I'll just end this here. Thanks for watching so far. Really mess with adding signs. It's kind of fun, actually, to demonstrate the Fourier transform in a simple sense. You can also try integral stuff, but just know that is the idea behind it. And next few videos, I'll do some calculus. So that'll be actually pretty cool. Thanks for watching so far.